if you remember, we started to talk about, we said the title of the topic is vector space, and we started to talk about the field, like what is a field and so on, right? And then we said, in order to check if something is a field or not, we have to check a few properties. And in short, it has to be closed in addition and closed in multiplication, right? Now, tell me if is
no.
Why?
Because we can find the multiplication inverse of numbers.
You cannot find the multiplication between the numbers?
1/0.
It's division, it's not multiplication.
Yeah.
So it has to be closed for addition and multiplication. 1 multiplied by 0 is 0, minus 1 multiplied by 1 is minus 1. So all things exist. Division is we don't care about the division. And do we have the unit for the multiplication? 1 multiplied by 1 is 1, 1 multiplied by minus 1 is minus 1, 1 multiplied by 0 is 0. Do we have a unity for addition? Do we have 0 for addition? 0 plus 0 is 0, 0 plus 1 is 1, 0 plus minus 1 is minus 1. Now, question is that, is this a field? I need a better justification if the answer is no. I need a very solid statement if the answer is yes. Let's start by addition. Okay? Let's start by addition. What was the addition of saying? It said that if A and B belong to F, then, not if we can say that for any A and B belonging to F, then A plus B is also inside our field, right? True? Mm-hmm. This is the definition of being closed. Now, is this valid for this set?
Yeah.
We want to show that no. A is equal to 1, B is equal to 1. So let's see if A plus A belongs to F. Because it doesn't tell you that A and B cannot be equal to each other, right? So it fails. What Hassan said was true, but wrong description. And the description should be in this form, that we need to have always the inverse element also inside our field. And the inverse of 0 does not exist. Division, we don't care. We don't care about the division. We don't need to be close for the division. But the inverse element should exist. And then, which obviously the inverse does not exist for case of 0. But easier form is this. So, we understand that this is not field. Now, the title of the topic of this chapter was a vector space, so let's start to define what is a vector space. A vector space over, or we call it under, field F is. So what do you expect this vector space be? What was F? F was a set of numbers which had some properties. So what do you expect the vector space be?
Set of vectors.
Set of vectors is a set of vectors which have a set of vectors which has the following properties. and these properties are on the addition and multiplication as we were expecting to see. The first, okay, and usually we show the vector space by capital V. And I write it like this only, this is not the notation of the class, the book, this is my notation, because my capital V and my lower v are very similar to each other. In order to show that this is a vector space, I show it like this, okay? So, property 1. For any u and v belonging to V, then u plus v belonging to V. Remember, u and v are vectors now. They are not scalar. They are like, I don't know, u and v belongs to Rn. Okay? They are vectors now. For any u belonging to V, and for any c belonging to F, then Cu also belongs to V. And usually, if a vector space, friends, if the vector space is on the field F, we show it like this: the vector space and the field. So we understand that the constant should belong to this field, and the vector space, this vector should belong to this vector space. U and V belonging to V, then U plus V is equal to V plus U. U, V, W belonging to V, then U plus V plus W is equal to U plus V plus W. I mean, very obvious things that we knew it from before, but now we will check all of these properties. For any U which belongs to V, there exists a 0 belonging to V that U plus 0 is equal to 0 plus U is equal to U. You remember we said that if A belongs to F, there exists a 0 belonging to F, that A plus 0 is equal to 0 plus A is equal to A. Can you tell me that what is the difference between this 0 and this 0?
One is a 0 vector.
This 0 is a 0 vector. This one is a scalar. For example, if V was R3, if V was, for instance, R3, then R0 means that is this. Okay? If for any U belonging to V, there exists a minus U belonging to V, where we have this: U plus minus U is equal to minus U plus U, which is equal to 0. Which is equal to 0. For any U and V belonging to V, and A and B belonging to F, we have these two properties: A plus B multiplied by U is AU plus BU, and A multiplied by U plus V is AU plus AV. With high probability, you remember all of these formulas from high school. And we never said that, we said that, oh, this is a fact. This is a fact. Because you were always facing with a vector space. And here we will see lots of things which are not vector space. We will do examples, we show that so many sets that we are defining are not vector space. The reason that we are trying to talk about vector space is when we want to find a solution of an equation, a set of equation, then we will prove today, we will see that it has to be a vector space. Then we start to talk about column space, null space, which are very essential because in computer science, everything is being described by using this column space, which is kind of a subset of the vector space. So there is a story behind all of these things that we are talking. So till now in high school, in undergrad, everything that you had was by default a vector space, so we were just writing these properties, right? Now we understand these properties are only valid for the vector space. If it is not a vector space, what can we say about these properties? If U and V are not a vector space, what can we say about the property of 1 and 2? Dana? If U and V, they are not a vector space, what can we say about property number 1?
No, probably it will not apply. It will not work.
We don't know. We can come with an example that it works.
Mm-hmm.
We can come with an example that doesn't work. Probably it won't work. In other words, we cannot write this. Mm-hmm. Because one counterexample is enough in order to say that this is not the general rule. So, and you can come with millions of examples which is not a vector space, and this property is valid, or this property is valid. But till now, in all your previous classes, we always said that this is valid, naturally they were valid because we had always the vector space. So we are starting to see that what will happen if it's not a vector space. Now, two more properties that we have to discuss is if U, for any U belonging to V, and for any A and B belonging to F, then we have A multiplied by B U is equal to AB multiplied by U. And for any U belonging to V, there exists one belonging to F that 1 U is equal to U, 1 is equal to U. So, as I will erase the board, I want you to track these 9 properties because we will solve a few examples about checking if they are vector space or not. And you have to check all the properties. Because if one of these 9 failed, then the V is not a vector space over the field F. Remember, V, note, V and let's say F1 may not be a vector space, but maybe we find another set of field which might be a vector space.
Is there an example of that?
a very simple example is when, let's say, V is restricting us to a Cartesian xy plane, and F1 is a complex number. And then when F2 is a real number, then we are okay. So this scenario can happen that we will not be able, the vector space is a vector space for one field, but not necessarily vector space for another field, right? So let's write down a few examples. The column vector Rn and the field R always vector space. Matrices, real valued matrices over real number, always vector space. Remember, a matrix is a vector, right? Ike, this is a question for you. The set of non-singular matrices over R. You tell me, is it a vector space or it is not a vector space? Well, maybe Hassan helps you. What is a non-singular matrix?
They have inverse.
The determinant is non-zero. The determinant is non-zero, which means the inverse exists. So, the question is that we have sets of all non-singular matrices that we have in R 2 by 2. So all non-singular 2 by 2 matrices, and we are over R. We want to see if it is a vector space or not. Like you have 50% of winning.
Yeah, it's a vector space.
It's a vector space. Pri? Do you agree with him?
Mm-hmm.
Okay. Dana?
Mm-hmm.
Hassan?
Yeah.
Oh, you will fail. It is not a vector space because we have a very simple example. 1, 0, 0, 1 belongs to RB, right? This is non-singular. What's the determinant? 1. And minus 1, 0, 0, minus 1 is also a very famous non-singular matrix. Right? What was property number 1?
U plus V belongs to...
Let's see. What's the result of this addition?
Zeros.
You tell me. Ike, does it belong to me? No. Obviously the determinant is 0. Obviously this is a singular matrix. So, one example for one of the properties enough to say that this is not a vector space. This is not a vector space. But actually it was quite obvious to see that non-singularity is a very fragile condition. It's very easy to break it, to make it singular. Because, what was the property number 2?
CU belongs to the
CU should be also in the vector space. Is there any condition on C?
Still belongs to the
Sorry?
belongs to the field.
But, so there is no specification that it cannot be numbered this. So what will happen if C is 0?
It will be 0.
Non-singular.
So the question was the set of non-singular two-by-two matrices, but then it's not clear if the whole entire vector space should be non-singular.
No. This is the question. Is it a vector space or not? The set of non-singular matrices over R cannot form a vector space.
So
Look, the question is that, does these things make a vector space? And then you say that, it fails, so these are not a vector space. These are only sets of cool matrices that we love. That's it. I can see lots of doubt in your face. Now, what's your question? I mean, what is like bothering you?
Yeah, I guess you tried to clarify it out.
So I was just thinking. So, what is the typical way to prove if it's a vector or not?
Well, typical way is that you have to go through all the 9 property and show that they are all true and valid. For, let's say, for number 1, property, let's look at if it is a vector space or not. First property, any vector of Rn plus any vector of Rn. Do you know how to you have to prove it in general? I mean, I will write it down. Can I erase this part? I already have written it, but I want to prove this. Let's say property number 1, which was saying that for any U and V belonging to Rn, we have to show that U plus V also belongs to Rn. Let's see if it is true. So we have U1 till Un, and we have V1 till Vn, and we know that they belong to Rn, right? This is the U and V. And then U plus V was actually U1 plus V1 till Un plus Vn, which is U1 plus V1, we call it alpha 1, a number. It's a number. This is alpha n, which belongs to Rn. First condition, okay. Second condition. Let's say that the constancy belongs to F, and U, which was U1 till Un, belongs to Rn. Then Cu is Cu1 till Cun, which is, again, call it, I don't know, beta 1 to beta n, which belongs to Rn. Right? You can expand it and do it for this one. You can easily see that this, do you want me to show that this is also valid? I'm showing the number 3 also, but for the rest you can just simply expand it. We have U1, Un, and V1, Vn belonging to Rn, right? Then we have U1, Un plus V1, Vn, which was U plus V, is equal to U1 V1, U1 plus V1, Un plus Vn, which is equal to V1 plus U1, Vn plus Un, because we know that 2 plus 3 is equal to 3 plus 2, right? And this is equal to V1 till Vn plus U1 till Un, which is equal to V plus U. So the condition is right. You can do the same for all other things.
But actually, in the example of the non-singular matrix,
Yes.
We couldn't prove that it's not a vector space unless we could find some numbers. I mean,
Yeah, well, you know that if you want to prove something, you have to completely prove it. If you want to disprove it, you just give one counterexample. One single counterexample is enough in order to say everything is false.
Okay, so if we have a specific condition to check if it's a vector space or not, we need to find some numbers to check if it's...
Yeah, I mean, theoretically, I mean, this one, the example that the previous example of non-singular matrix was kind of obvious. So you were looking for something specific. But let's say it wasn't obvious for you, and you think that it's a vector space. Before say that it's a vector space in the exam, you must write all these steps one by one till the end, till the ninth one, and then when everything is okay, you say that this is a vector space. Because giving this sentence, it is a vector space, it is not a vector space, it is not enough. Because it's a 50-50. You understand? So, but you have to prove it. Even if you say this is not a vector space and you do not provide an example, it's still acceptable. You have to provide a counterexample. So, if you are not sure, you can start from condition number 1, number 2, and go till the end. And if everything is verified, that's done. A few cool things that you have to consider, you know, for example, in condition number 2, 0 is always a tricky thing. You have to check on 0, right? Because for the singular matrices, it works very well for all numbers. 0 is the one which destroyed everything, right? 0 is the one which destroyed everything. And also for the addition, you know, for the addition, let's look at the singular, this non-singular matrix of 2 by 2, and mathematically see what we can say about the addition of two of them. So, in previous example, of non-string matrices, we can say this. Imagine U, which is U11, U12, U21, U22, belongs to my V, right? And V, V11, V12, V21, V22 belongs to V. Then for U plus V, which is U11 plus V11, U12 plus V12, U21 plus V21, and U22 plus V22, we cannot comment anything. Why we cannot comment anything? Because we know that U11, U22 minus U12, U21 is not 0. V1, V11, V22 minus V12, V21 is non-zero, but U11 plus V11 multiplied by U22 plus V22 minus U12 plus V12. My U's and V's are look like each other, but I'm sure that you are clever enough to distinguish them. There is no logic from here. You can get to this conclusion because you can even expand it. Let's say you want to expand it. So what we get is U11 V22 plus U11 V22 plus V11 U22 plus V11 V22 minus V12 U12 U21 minus U12 V21 minus V12 U21 minus V12 V21, which is equal to, look, U11, U22 minus U21, U12. So let's see what I have written. This term I have written. This term I have written. Plus V11, V22 minus V21, V12. I have written this. I have written this. Plus U11, V22 minus U12, V21 plus V11, U22 minus V12, U21. Look, Rick. This is 0. This is definitely not 0. This is definitely not 0. Okay? Which means that these two additions is number alpha. But this one, can you guarantee that this is not equal to minus alpha? No. Because we cannot comment. I mean, maybe, maybe not. So we can come to the example that it is. We can come to the example that it is not. Because of this, we cannot comment, so it means it fails. Because if you want to say something solid, you have to be able to comment. We cannot comment, so it fails. But instead of writing all these things and come to here and say that we cannot comment, we just give one example, which makes things to be much easier.
So basically, if there is one particular example we have in our head or something that disproves it, we could just put
Yeah, definitely. It's called counterexample. You know, proof. Disproving by counterexample is a very famous method in calculus. So if somehow you can see it, that example, just put it in. That's all right. But with with 1 million example, with 1 million, with 1 zillion example, you cannot come to a conclusion. Because one number is enough in order to say. For instance, how many even numbers do we have? Infinity. And then we say that all even numbers are non-prime. They are not prime. Like 4 can be divided by 2 and 4 and 1. 6 and all other things. And we have infinity many examples which are satisfying this condition, except one single example. Which is number? 2. Number 2 is the only even number which is prime. And the other rest, which means infinity many examples, which proves that the all even numbers are non-prime, this theory will go away because one counterexample is not. So we have to be very careful. But usually the counterexamples, I mean, in this type of questions, are not like very difficult to find. In other words, you don't need to multiply by a Neperian number and divide it by pi to come to the result. It's very easy. I mean, easily you can multiply it by 0 and come up with a solution. Or just add it with its own inverse, or this type of things, you know, very easily you can see it. Now I have one more example, which I want you to think about. It's example number 1, 2, 3, 4. Set of vectors in the first quarter of two-dimensional Cartesian coordinates. Or on field, we need to write field, we know that this is a field, on R. So this looks like this, Rn to R, but this Rn is not all Rn's. It is the ones which are only in the first quarter. Do you know what is the first quarter, Dana?
Yes.
Ike? Pretty, I mean, it was this, right? The Cartesians have 3 quarters. First, second, third, and fourth. It means this. It means this. So, is this one a vector space? Quickly, go over the condition number 1, the first condition. Vector u plus vector v. Any vector in this quarter, added by any vector in this quarter, what is the resultant?
Would be the same.
Must be in this quarter. Must be in this quarter, right? Why? Because this quarter is a positive quarter. You have a positive number, you add a positive number, you will get a positive number, and this is the only place that we go, everything positive, right? What was the second one?
Constant.
A multiplication of a constant to this vector. We have a vector in here, we have a u in here, and I multiply with a constant. What about the result?
It's still there.
Not necessarily.
Why?
What if the constant is number -1?
And then it's not.
It's not there, right?
The constant has to be in.
The constant must be in R.
Oh.
The constant must be in R because we are defining over R. So if we multiply it with -1, which is not in the first quarter, so this is not a vector space. Right? Ike? No doubt? Cool. Because now I have my next question to you.
So if we define